Hello everybody, and my name's Lyndon Smith, and I'd like to say a few words about my new book. And just starting up from the beginning here, you can see that the title of it is Why You Can't Catch a Rocket to Mars. And this is a book I've got coming out really talking about science and society, and hopefully in a light-hearted way. So hopefully you'll enjoy it and find it enjoyable to read and amusing with any luck at all. So, it was about 5 years ago in 2015 when I was teaching a course up at the university, and a student said to me, "Today's the day when Marty McFly has got to come back on his hoverboard." And I said, "What's that about then?" And they started telling me about Back to the Future 2. And apparently flying cars are on the cards in this future. And this is what they imagined in 1985, that 2015 was going to be like. And I said to them, "Well, you must be really disappointed then, because we just got to get into the diesel bus now to get home." And they laughed. So that started me thinking about where we got to with science and technology, in recent years, and maybe why developments haven't been quite as dramatic as many people have expected in the past. I mean, Peter Thiel, the American technology, said we wanted flying cars. We got 140 characters, which I thought was quite a good summary of the situation, really. So because technology hasn't really developed, at least in terms of machines and so on, it's developed in terms of the internet quite well, but in terms of machines, it hasn't really developed. We're still driving around most people are still driving around in petrol and diesel cars, and we haven't got the technology to get to Mars easily. I mean, you can just about manage it in a rocket, in a chemical rocket. It might take over half a year to get there, cost over $500 billion, but it's not completely impossible. But it isn't so. It's not exactly an affordable and convenient way to get there at the moment with the technology we got. So, can we look to the past? Can we look for inspiration to the past? Well, I say yes. Because when these sort of engineers in the past built things, they really built them to last. They were looking to the future. They didn't build them just for a couple of people ambling across the bridge that they had going on at the time. They were looking to the future, which is something you need to do in transport, for example. I think it's well known that you need to look to the future, but for some reason we don't tend to do that. We build a motorway just about sufficient to handle the traffic it's got, and then we have to continuously upgrade it, which costs about 20 times more than if you just built it to the higher spec. But look at this. This is the iron bridge that Abraham Darby III built across the Severn in Shropshire. And in 1781 it was opened. And it's still operating now without any modifications, really, some basic maintenance. And the same is, of course, true of the beautiful Clifton suspension bridge, which links Clifton in Bristol to Lee Woods across the mighty Avon Gorge. And that's very aesthetic design, I think you'll agree with this one. With them both, in fact. But this is, of course, a suspension bridge. And again, very minimal work required on it, a little bit of maintenance, no major strengthening, and it's still carrying vehicles, so many tons of vehicles. So that was built, of course, by Isambard Kingdom Brunel. And when he died, his good friend said, the commercial world thought him extravagant. And although he was so, great deeds are not achieved by men who think about the cost of every thought and deed. And I think that's true. Nowadays, you need people like this, I think, these Victorian romantic engineers who look to the future. We need that kind of inspiration to think about what can we do with really future-thinking projects now. And of course, both of those bridges ended up lasted without any problems for really a vast amount of time. So that's the future. That's where we can take our inspiration from these guys who have real vision and real ambition and aspirations. And of course, I couldn't talk about this without talking about Bristol and engineering, without talking about the Concorde, which of course was built in Bristol as well as France. And the only commercial airliner to have flown scheduled supersonic flights. And of course, it could fly at twice the speed of sound. I mean, it could cruise at twice the speed of sound. And can we imagine anything more futuristic and ambitious than this? It must have been so much excitement in Filton when they were developing this in the 50s and 60s and 70s. I mean, look into the future or what? They would have thought we'd all be flying around on a supersonic aircraft by now, but we're still toddling around at 0.8 of the speed of sound in these bulky jets that we fly around in, because it's a little bit cheaper. Well, it's quite a bit cheaper, I suppose, than flying the Concorde. The only problem with this technology is that it was a little bit inefficient, I suppose, because these turbojet engines it used are not as efficient as the turbo fans. But I thought that was a really great picture from the Southwestern News Service, really capturing the two really amazing Bristol icons, the Concorde and the Clifton suspension bridge. You can see how many people were out to see this Concorde's last flight. And now, of course, you can see it at Filton. It's in a museum there. But that's a fitting epitaph for a fantastic aircraft. So in the future, in the past, people were looking to the future. And we need to look to the future, I think, a bit more. So now thinking about Newton, of course, I'm thinking about the promise of science. What have we got in terms of the promise of science? Well, science is a very powerful tool. I certainly like it. You can do very complicated and difficult things. Newton's 3 laws of motion, the basis of the whole of mechanics that we use in our everyday lives, cars and trains and everything else. And but then again, the development of cars over the last 100 years seems to be a bit modest, actually, doesn't it? In terms of they're more efficient and more reliable, but they're using the same old internal combustion engine. So we need some more development. I just put a little note on the side there because that's me at the science at Madame Tussauds in London, of course, and there he is with his prism. So he discovered that white light can be split into a spectrum of colours by use of a prism, and that enabled us to determine the chemical composition of the stars, which is something pretty amazing, if you agree. So people have these breakthroughs in the past, and we ought to be able to do something similar in the future, really. And so to get new types of machines, I mean, if we want revolutionary cars, we need breakthroughs generally in science, materials, and physics. And recently, developments in physics may have been not too dramatic in recent decades, perhaps. And I was wondering, why is that? Now, of course, one reason is that physics is a hard subject, I guess. Nature does not give up her secrets willingly. So that's not much we can do about that. That's just the nature of it. I think also that there's a general underappreciation of the benefits of scientific research, what it can benefit, how it can benefit us, what it can offer society. You don't hear that much about it in the media, I don't think, really. And I also feel that science is becoming dogmatic. And this is what I try to show with this diagram, really. A strong preference of methodological reductionism. So what we got there is we're trying to break everything down into like cogs, into little parts that are working, and that's how we'll understand how the overall system works. But it may be that doesn't actually help us in a way that's useful for getting technology off the ground in a big way. And the other thing I got, of course, here is that rigorous mathematical treatments are often viewed as more essential or important than relevant scientific arguments. And I think that's true. If you look at journals, they're very, very keen on putting a lot of maths in, whether you need it or not, really. And they're not too keen. They wouldn't accept a paper if it put a rigorous analysis of the arguments and physics arguments which didn't have some maths in it. So there's this. I'm not saying maths isn't useful. It's an extremely powerful tool in physics, but to put it before the physics argument seems a bit amazing. Someone who had a few views on maths actually was Edgar Allan Poe. He wrote about it in his short story, The Purloined Letter. If you get a chance to read that, he wasn't too sure that maths had a general applicability, and so it might be maybe he was on something there. So we need new breakthroughs in science, and particularly in physics. And to carry on about what might be holding it back, I've got environmentalism. Now, of course, we need to look after the planet. We need to tackle climate change and so on. But we need to realize that also advanced technology is what's really might help us to really solve these environmental problems. I mean, I've got this thing I say to people, I love reading books and watching history programs, but such things are not going to save the planet. For that, we need science and technology, and particularly physics. And political correctness, everybody's got to be treated fairly, but if we extend that to pretending the situation is different from what it is, that's the opposite of physics and science. With science, you're seeing things as they are. And if you don't want to recognize what problems you've got, then you stand about zero chance of being able to solve them. The other thing I got down here, of course, is an explosion of administration driven by risk aversion. It may be that risk aversion is one of the big reasons why Peter Thiel said we're disappointed we don't have the flying cars. He certainly thought so. If you're completely risk averse, you're not willing to take a chance on anything or invest in things, then you won't be getting these big breakthroughs in science and technology, most likely. You'll be obsessed with ethics, and ethics and risk assessments are important, but if you absolutely build it up into a huge area, and other areas of administration as well, then this reduces the time and effort that can be spent on research, I feel. And down here, we've also got a general lack of collaboration between university research departments and companies. And this is quite a big subject, which I tried to talk about in some detail in the book, but there's a sort of cultural difference between universities and companies. And that's something we could talk about a couple of hours about, or several hours about, and spend the whole book on, really. But I do go into that little bit of detail. So these are the first introduction to some of the things that might be holding science and technology back. Talking about how we can solve some of the problems I talked about a minute ago, one of the ideas of getting better developments in science and technology is to get over the valley of death, really. And what is the valley of death, you might say? Well, this is a slide not of the valley of death, but of Death Valley, which is a very interesting place in eastern California, if you get a chance to go there. So, where the warmest temperature ever was recorded at Furnace Creek some time ago. Now, it's just what the Valley of Death is a region between where you are with your idea and your technology and so on, and where you want to get to in terms of getting it out to people so they can actually use it to get huge impact, a new type of system, something people can use to help solve their problems. And so we need to commercialize the technology. We need to have involvement of a company, and we need to develop it for the industry, develop it for the public, or wherever we're trying to sell it to. And that is a tremendously difficult thing to do, surprisingly difficult. And that's why it's called the Valley of Death, because many people sort of fail, or their idea dies on the way to go into the market. So what we've got at the moment is a system for winning grants, as it says here, to do research. We get big incentives to win funding, but the problem is that there isn't such a huge incentive, really, to actually get great work and high impact. It's just the way that everything's arranged. And also another problem is that there are cultural or behavioural barriers between academia and industry, and this makes it rather difficult for academics to interact with industrial people. But how can we overcome these problems? Well, I was also thinking another area I was thinking of is, I talk about how we might overcome them in the book, but what I'm trying to do here is cover topics that are mentioned in the book in some depth. Schools and teaching is another area. Teaching is an estimable profession, and it's great. I mean, I know so many great teachers, and people who devote their lives to helping others and realize that in doing so, they're helping themselves, really. What a fantastic profession. But it is an intellectual profession in itself. It doesn't need, you don't need to take it further. Teachers are intellectuals in terms of what they need to do in terms of intellectually. They don't need to become abstract intellectuals or business people. I mean, which you sometimes see, to be honest with you. Sometimes headmasters can sometimes have the business person role, the executive role, but it's a head teacher. It's a teacher, so the teaching is the important thing. That's why headmasters should really teach, I feel, and to some extent. And the job is big. I said here, the job is important. You don't need to big it up by making out your general intellectual, abstract intellectual, or a business hotshot. So, and it also applies. You don't need to big things up. It also applies to physics and maths. They already have enough gravitas. They're fantastic subjects. They're powerful subjects. They don't need to be bigged up all the time. In A-level maths, there's not much application on applications. There's not much emphasis on applications and real-world needs. There's an emphasis on abstract, on closed-form, complex solutions that many of which many people are not going to need to use in their later lives in work. And there isn't much emphasis on statistics. I mean, when I did it at A-levels, there was no statistics in it. So when I did a PhD, I had to learn all this multiple regression and so on from scratch, which was difficult and a lot of work to it because it just wasn't covered. And so, I think a lot of the time also there's a lot of emphasis on new physics, quarks, in-depth analysis of quarks. What chances are there of that being useful in one's career? And abstract mathematical techniques, or new approaches that are fashionable for one reason or another, like multiple answer questions. Good grief, I could spend an hour talking about that. But there are many reasons I feel why they're not really a good approach, which I go into in the book in a lot of detail. Easier for the person to mark, but not really better for the learning process. So this is the kind of things we're talking about. But what is the importance of being an engineer? How can we talk about the importance of being an engineer? Well, I talk a bit about engineering because I'm from a family of engineers. My wife is an engineer, as was her father. My brother's an engineer, as was our father and his father after that. Being an engineer has a meaning of itself. And anyone who wants to understand the significance of the role can, I feel, as it says here, learn a lot from popular culture. I mean, Scotty from Star Trek, and there he is. in the Jeffries tube on the Enterprise, and with bones behind it. But didn't he say so much about the pride of being an engineer? You know, it was like the ship was his baby. You know, he took so much pride in his work. This is what the new developments, the new ship, the excitement of the new device. It doesn't have to be a starship, it can be anything. If we look to the past, we had Brunel's with his broad gauge. I mean, near to where I live here, there was a broad gauge railway going by in 1840 or something, and that was a 7-foot gauge. Now, if we had 7-foot gauge around the country now, we could probably go to 250 miles an hour on our trains. But what do? We went to standard gauge, a bit cheaper and easier. And now we're having all sorts of problems tootling around on this relatively narrow gauge when we want to go quickly. So in the long term, you know, I know there's a lot of emphasis on beam counting nowadays, but it may learn in the long term lead to all sorts of limitations and probably costs that you don't expect. And everything will end up being more expensive if we're not careful, if we don't take a longer term view of the needs. So, you know, this next slide might be a bit controversial, sorry about that, but I put down here, is a technical science PhD, technological one, more valuable than a humanities PhD? Well, yes, as far as I'm concerned. Well, why is that? A few questions are here, a few answers are given. Science and technology can offer the potential in many situations to save your life. I think with this COVID pandemic that's been going on recently and all the tragedies associated with that, we find that some inspired people who are hardworking are developing these vaccines, and they're going to save probably many millions of lives. There's a good example of it. Science is objective, while the arts are subjective. In science, you can show things objectively. You can't really in the arts. It's all subjective. Science can be proven to have real value, whereas the arts cannot. Here's an example. I live in Somerset, many miles from a shop. I have to drive every day in my car, which is a product of science and technology, to survive. I also like the paintings of John Constable. I even tried to dabble in oils myself a little bit, and this is what I did of a scene on the river, a view on the Stour near Dedham. But I can't prove that Constable's or anybody else's paintings have real objective value. It's just that I like them. I can't prove they have real value. And the other thing I think I mentioned just on the end here is modern art, the Turner Prize. I think this could be a good example of why the science is more important than the arts. I mean, we need the arts. Man does not live on bread alone. But some people think the Turner Prize is great, some people think modern art's great, and some people think it's a lot of nonsense. It's hard to prove it isn't a lot of nonsense. It could just be a case of emperor's clothes. And we have in our village here the Turnip Prize, which is awarded every November for in a sort of parody of the Turner Prize. And there's some great entries in there. You have to spend a minimal amount of effort on it. It has to be sort of rubbish you're dealing with. I want to enter something in that competition, really. Fantastic. So much of the problems. What are the solutions? Can we be certain that there will be attainable solutions to the above complex problems? Well, maybe not all of them. Many of them are got to do with sociological factors, historical and cultural situations. At the same time, we've also got the black swan, of course, where things come along randomly, like COVID itself or 9/11, which can have very far-reaching and influential economic, political, and social effects, and we can't predict them. So we can't do that. But then again, maybe we can model. We can model certain things. We can do modeling and analysis, which really will help us, even though we can't cover everything. Of course, we've got a lot of complex problems. Multi-factored modeling analysis will be required to get solutions to all sorts of non-trivial tasks that we want to perform using robots, for example. And up to now, it's been considered too difficult and complex for reliable modeling. And that's because we've been trying to use closed-form math solutions or limited solutions where we need to structure the environment heavily to get any kind of result. You don't want a robot solution where you have to put more effort into structuring the environment, like robot vacuuming, than you would if you just vacuumed yourself. See, there's no benefit then, really. But all this is changing now, principally through the exciting developments that occurred in artificial intelligence, and particularly the technique known as convolutional neural networks. And what you can do with CNNs is that you can have very powerful pattern recognition devices, and they can be used to identify features of interest in complicated sets of images. So we can solve them, thereby, complex problems that have previously been considered too difficult for anything but a human solution. For example, a scene like this, the CNN can automatically identify that's a car, that's a dog, that's a human, and then it can react. And it also can deal with all sorts of changes in light and point of view and shadowing and everything else. they can automatically, another important point, they can automatically learn what a dog looks like. I don't have to tell it, it can do it itself. And this is an important point. We don't have to tell the CNN what it looks like, it works out for itself and thereby gets a more accurate and reliable idea of what it is and therefore can work better than if I try to tell it. So this provides two strong advantages. Firstly, the vast amount of work that used to be needed to handcraft features of dogs is no longer required. I don't have to tell what the dog looks like. Secondly, the computer generates its dog feature purely based on the images it's been given a dog, so it's more reliable, as I say, than if we told it what a dog would look like. CNNs are robust and remarkably reliable in recognizing, in fact, all sorts of objects. Even when the training and test data has been used, have been given for those objects, contains a good deal of variation, such as shadows or changes in light levels. We're talking about convolutional neural networks, and they're able to solve all manner of problems beyond simply detecting the presence of dogs in images, of course. We've got great potential for solving a wide range of formidable problems, it says here, that will be critical for advancing science and technology. Now, although one characteristic that's often associated with CNNs, as mentioned above, is a need for extensive training data, there have been developments in recent years which can be used to very much reduce the amount of data a CNN needs before it can start producing useful outcomes. And I can't go into detail here about these. I do talk to them about in the book about them a bit. And the two techniques are transfer learning and data augmentation. This is an example of a CNN. You see, this is the kind of image you put into it, where you get a bit of a busy image of, and there's actually some dockweed, which is kind of important to detect and get rid of. So with this, the machine can automatically recognize this dockweed and they can segment it, as they call it, which is identify the region where the weed is. And then we can fire a bit of weed killer right at that, rather than spraying weed killer everywhere. Now that has the advantage that we don't waste money on the weed killer, we don't damage the environment, we don't kill the clover, which is a broadleaf plant which is good for the animals and the soil. And so there's all sorts of benefits. In the future, people will definitely be doing this all the time and will be good for them and the environment. But what we need to do, I think, is take a systems-based approach and think big. This is what I feel we need to do to get real technological breakthroughs in new autonomous systems. We need to take new types of systems to deliver novel and advanced capabilities in the form of automated solutions to complex and significant challenges. We need a revolution, really. We don't want to just tinker around the edges. We need new dramatic technologies that can solve all sorts of complex business problems. And one example of this, of course, is getting drones to deliver items that we order online, where we combine GPS and advanced vision. That's where the deep learning comes in, analysing the vision images, really. And so we need to develop our own systems which capture images as in our application, and then we use all that data in the AI and deep learning to develop artificial intelligence to help guide that package into where we want to drop it off. So other topics that we covered, but I can't go through here in tremendous detail about everything that I talk about in the book. Of course, all I'm going to really mention here is some of the areas that we cover in the book in some depth. So can computers be used to more effectively direct technological development? So that's technology. Now, how could we use deep learning to aid technology? There's a few ideas there. And then going beyond technology to science, how might we use computers with data and metadata, perhaps, to really help us in our scientific understanding? So that goes beyond the engineering, sort of into the basic science, which would help us develop the engineering. And then we got the nuts and bolts of a rocket to Mars. That's talking about some of the technologies we could use to actually get to Mars more cheaply and easily than we do at the moment. For example, things like mass accelerators. We could use them to get vast amounts of material up into orbit. We could assemble it up there into a big sort of space station launcher, and then launch from orbit, which would be much cheaper and easier than launching from the Earth. So other technologies also that could help us with that in the longer term are also explored there. Then there's quite a large section in the book on potential and definite threats and possible responses. And the ones that have gone into are Brexit, of course, contact with extraterrestrials, which Carl Sagan was keen on, but Stephen Hawking wasn't, for various reasons. Near Earth objects colliding with the Earth, bits of rock flying around the solar system. There's quite a few of them, thousands of them. There's a possibility some of them might collide with the Earth at some point. Viruses, of course, which is a big one, which has been in everybody's mind with the COVID pandemic. And then global warming, which is probably the most serious of all the threats we might have to deal with. And we don't know if we can deal with it or not. Hopefully we can. Talking a lot about different options in relation to that. And the idea of not being able to deal with it naturally leads on to the next sections in the book, which are more to do with advanced technologies that we might help us to survive as a species, even if global warming is impossible to control. So that leads on then to what the future holds. Developments in science and technology are discussed first, involving the past, of course. Then I talk about the miraculous quarter of a century, which I feel was from 1939 to 1969. There were tremendous developments in that period, and it's interesting to think about why they were so dramatic and why there hasn't been that much happening since, apart from the internet and smartphones, for example. And then talk about the present, what we can do now, what we could do with relatively modest technological advances right now. Things like the automatic weeding I was talking about, and other all sorts of applications in medicine and security and so on. And then what we might be able to do in the near future. Things we could do now might be like detecting people using 3D face recognition, which is something we worked on the London Underground, so people wouldn't have to mess around with tickets and pins. So in retail, we could do that now, really, more or less. In the near future, we could do things maybe like automating certain medical robotics procedures. At the moment, they're done teleoperated by surgeons, but maybe we could automate certain procedures in the near future. I mean, the next few decades, I say near future. And then thinking about the far future, which is really interesting. The far future, what are we looking at in terms of transport and robotics? And these are big subjects. And of course, as we get more into the farther future, things get a lot more difficult to predict what's going on. So, transport, there are all sorts of possibilities for high-speed transport. I mean, thinking of Star Trek, the transporter mechanism, that would be traveling at the speed of light. So the possibilities or otherwise of that sort of thing I talked about, matter transportation. And then robotics is an exciting field. Here, showing a robot here, but robotics is a field where there's so much that could be done and so many exciting possibilities that could be on the horizon for the farther future, especially when linked with AI, big developments in AI. Thinking now about the very distant future. So one interesting thing I think I was thinking about from the film Forbidden Planet was the elimination of the need for instrumentalities. And this is interesting, whether you could read people's minds and then use that to help interact with the physical environment. And it's something that Elon Musk is looking at with his Neuralink company, reading sort of brainwaves and then using that to help people who are locked-in syndrome, for example, to communicate and do things. If you could link this with robotics, you might be able to do all sorts of impressive tasks just by thinking about different things. You can imagine on a building site, someone thinking about moving a concrete slab up in the air and then their thoughts being read and the crane lifting it up for them. So there's all sorts of fantastic possibilities with that. It's not that far, and it's not that amazing an idea. As you can imagine, at the moment people are reading brainwaves and doing some things with them. Elon Musk with his company has got a pig brain implant and is able to read certain conditions. So that's something for the future. Time travel is an exciting idea, of course, very popular with fantasy and science fiction authors. But what are the physics, from the physics point of view, the real chances of being able to travel into the past and the future? I talk about that quite a lot of depth in the book. I got the power, Nikola Tesla used to say that power ought to be available to everybody for free, and he's probably right, but it's easier said than done. But I talk about power sources, nuclear fusion, and the potential for that, the limitations of nuclear fission, and the great promise of renewables, for example, the Severn barrage and topics like that. I've talked about in quite a lot of depth, especially in relation to global warming, of course, being an important factor there. Then talking about, it's a material world, talking about what have we got there from the point of view of different materials. Because often they say that breakthroughs in materials lead to big breakthroughs in technology and machines and systems. At the moment, there's a lot of emphasis, of course, on things like nanotechnology and things like graphene and other materials. And very, very strong materials might, for example, enable us to build a space elevator, which would be 1,000 miles long, or tether, which would be many thousands of miles long. And as something was lifted up the elevator, it would start moving through space, and eventually, when you reach geostationary orbit, you just release it, and it would be in orbit, geostationary orbit. And this has been talked about by various people, and it's a fantastic idea. But the materials are not really strong. You could build one now on the moon or on Mars, but for the Earth, materials we've got are not quite strong enough. Kevlar is not quite there, so maybe we need something like graphene for that. Effects on, miscellaneous miracles. I talk about things like invisibility and immortality and things that people are interested in. That's the miscellaneous miracles section. And then effects on our society. It's all very well to have all these amazing things, technology that might be available, but what effects is it going to have on the way people live? And this is described and discussed in a little bit of detail. And that leads on naturally to putting all together the destiny of mankind. And things like if we could travel very quickly, very, very high velocities, then we might be able to explore the nearest stars. We might be able to explore into the galaxy a bit. So there's a lot of discussion in the book about the physics point of view, about how realistic that is. And it's an exciting possibility because, of course, as Ray Bradbury used to say, once mankind gets to Mars, we'll be safe. But if global warming is a really unstoppable, serious phenomenon, we don't want the Earth to end up like Venus. Or if it's going to do that, there's nothing we can do about it. We need to look for other planets, I suppose. So that would be a fantastic possibility of mankind moving out into the galaxy if we could do that. And talking about that, there's a man's future in the stars. I think Shakespeare said, man's future is not in the stars. What he meant by that is your future cannot be read in the stars. You have to make of your life what the best of it you can. You can't expect to read it in the stars. But although that's true, our destiny may be to go into the stars, for mankind to go into the stars. And that's a fantastic possibility, which I like talking about quite a lot and covering the book in quite a lot of detail. And then there's a summary of the predicted far future technological developments. So I put a table in. I said to start with, we can't guarantee any of these timescales. When you start talking about the far future and these kind of fantastic ideas, you can't expect to give any kind of realistic timescale. In fact, it'd be hard to give even a list of things that could be achieved. Nobody can look that realistically and accurately that far in the future, but it's kind of interesting to think about potentials, and I have a table of them in there which we talk about it. So the final section of the book is putting all together, the destiny of mankind. Man's future in the stars, I was just discussing this about Shakespeare, but what does it mean? What do all these technological potentials mean? And what might be the future of humanity or of mankind if we can make something of all these things in reasonable timescales? I mean, probably the most important thing, of course, is to avoid a foolish Armageddon where mankind destroys itself in a nuclear war. But there are some uses actually for nuclear weapons that actually might be positive. For example, you might be able to use a hydrogen bomb. I'm talking about rocks flying around in the solar system. If one was coming towards us, you might be able to fly out with a hydrogen bomb and let that off to deflect it a little bit, and thereby sort of miss the Earth. So you can imagine the positive and useful applications even for something like a hydrogen bomb. But what we make of all these potential technologies depends on how much we value them, how important we think they are, and how much we want to develop them, I guess. So that's something I kind of talk about in the book in quite a lot of detail. And some nice quotes by Stephen Hawking, who was quite keen on the idea of going off to Alpha Centauri, the nearest star, and see what was going on over there. He talked about it quite a bit. And then, so there he is, in fact. This is a scene from one of the episodes in Star Trek The Next Generation. And you can see that we've got Einstein represented, Data the robot, Stephen Hawking, and of course Isaac Newton. And apparently, as it says there, when Hawking went on the tour of the set, he saw the warp core in engineering and said, "I'm working on that." And to this day, Hawking is the only person to ever play himself in any episode of any series of Star Trek. So concluding remarks, then, as I say, are by Stephen Hawking. Remember to look up at the stars, not down at your feet. Try to make sense of what you see and wonder about what makes the universe exist. Be curious, and however difficult life may seem, there's always something you can do and succeed at. It matters that you just don't give up. I think that from Stephen Hawking is a very nice quote, very positive, very future-orientated. So that's the cover of the book then, and that's a few things I mentioned there that are in the book, and I hope they will be of interest to you. The book is available on Amazon, and it covers many of the topics that I've put in there. So I hope it gives you, I hope you find it interesting and hopefully enjoyable, and I hope it gives a few insights into a few technological developments that could occur. So thanks very much for listening, and all the best, and I hope the book is of interest to you.